Good afternoon, this is Schweitzer, and we're going to run a short little video here on, looking here, external versus internal. So this video is going to look at the internal factors that affect gases. Now, for the other two times that we've been dealing with internal factors, we're looking at, typically speaking, intermolecular forces. Now, intermolecular forces, let's give us a pen here. All right, intermolecular forces would be great, except gases, they don't really follow, they're too far apart, and they're traveling too fast, and sometimes they don't really interact all that much. So this section is going to deviate slightly here and talk about two other factors, which is, what's called an ideal gas versus non-ideal gas. That is really what this whole presentation is about. Okay. So, alright, so first of all, what is an ideal gas? What is a non-ideal gas? An ideal gas is essentially where there is no attraction, or repulsion between particles. And essentially, this is because the particles have a huge distance to size ratio, and they're moving extremely fast, and therefore there's just no time, or the strength of the attractions is just too weak to really cause anything difference. Now again, under what conditions would this thing start to fail? Well, let's slow them down, and let's get them closer together. So by slowing them down, you have more time for the attraction to take effect. And by getting closer, your force of attraction, which is the charge of a positive times the charge of a negative divided by the internuclear distance between them, if you decrease this, then even a small attraction can start to get larger. Alright, so what is a non-ideal gas? Well, a non-ideal gas is where just the opposite, where essentially there is attraction. So under what conditions are things most likely to be ideal? Alright, so this would be like colder temperatures, okay? Increased pressures. This is where now the particles, run that in there. The particles are forced to be close together under a large amount of pressure. So high pressures, colder temperatures, mean you're going to get a lot of particles in a small space, and therefore they're going to have more opportunities to interact between each other. Under what conditions would a gas more likely be a non-ideal gas? Well, this is kind of the same thing. So I guess I should say that under what conditions would a gas likely to be ideal? So I explained the conditions here where you're likely to be non-ideal. Non-ideal, would be one where we want them, we're looking to interact. So how do we get them to interact? We have colder temperatures and higher pressures. If we do not want them to react, no attractions, then we got to reverse that and get them really far apart and get them moving real fast. So that would be low pressures, right? And that means they're really far apart, they're not colliding a lot, and high temperatures. Another thing I might mention here is that some kids tend to think that all substance X is just ideal, and substance Y is just non-ideal. And this just isn't necessarily the case. It's really about, well, first of all, ideal gases. Sometimes I make the idea the sort of comparison. The ideal gases are kind of like unicorns. You know, my daughter loves unicorns. They don't really exist. Okay, don't tell her that as a 6-year-old. You know, they don't really exist. There's my unicorn here. So what does that mean? It means that technically there is no such thing as an ideal gas. There's always going to be some kind of attraction, even if it's very small. Okay, so it's kind of like a real generalization. So all things, you know, have some attraction. Some of them are just really small. So in this situation, keep in mind that this means that if all particles are ideal, then basically particles, okay, particles just act like particles. And the identity of these particles is of no consequence. So we have what's called an ideal gas law, which is like PV equals nRT. Do you see anything here that identifies the type of particle? No. So in this situation, it's not like all of a sudden one gas is ideal, one gas is non-ideal. Every gas, if given some conditions, could be allowed to attract a little more than normal. And we talked about that, where in the conditions that favor, so we're looking at any gas could become restricted to become a little bit more attractive or repulsive based on these conditions. Now, some particles are inherently more attractive than others, but we'll talk about that in a moment. So how does an ideal gas become non-ideal? Well, how do we get particles to start interacting? Well, we need this to go up. Now, these are the charges that are on the individual particles. I can't really change the particles. Okay, maybe they don't really have much of a charge on them. Maybe they do. But I can't change that. That's just inherently part of the particles. Only I can do is get this distance to go down. And again, that's by cooling, all right, lower temperatures and higher pressures. That gets this to go down, which causes this to go up. Even the smallest attractions, you get them close enough, they'll start to have a force of attraction or repulsion. Okay. All right. So ideal gas, are all gases that are ideal or not ideal? No. There's no such thing as X gas happens to be non-ideal ideal. No, it's not. That's not the case. Okay. Why do gases become or act ideal? Essentially, they're too far apart and they're traveling way too fast to cause a significant attraction. Now again, this idea here that you're thinking of, okay, is kind of what the basis of PivNert is on. So you'd find that PivNert really, sadly, if you get in lab, doesn't really work all that great. It only works under certain conditions. Okay, and we use it like it was written in the back of the Ten Commandments or something. It really, you know, in lab, it's got a very narrow range of decent results, because as you start changing conditions, gases are less and less ideal and more non-ideal. Why are these gas laws called ideal gas laws? We have this one. Why are they called ideal? Because in neither of them do we have the identity of the gases involved, and all gases are assumed to act the same. Okay? These are both considered ideal gas laws. But as we move along here, you'll find, okay, sometimes, again, if I have two particles that are going to interact, force of attraction equals Q times Q divided by distance squared. Now, another type of problem that will happen here is they'll compare gases. You got this guy versus this guy. Okay, so if we were comparing these two gases, which one, given the same distance and given the same conditions, okay, now if all the conditions are the same, then now we're looking at which two particles have the most inherent charges. Those are the ones that are going to most likely violate or deviate from what we'd be thinking of as an ideal gas. So in this case, the most increased intermolecular forces is going to cause your gas to deviate from ideal. So now it says, okay, we have these two gases, and they start to be cooled. Which one condenses first? Well, the one with the most intermolecular forces are going to start to have attraction first. Now you got to start walking your intermolecular mental path, your pathway. All right, dipole moment 0. All right, xenon hexafluoride, I believe that also has a dipole moment 0. So now we're down to just London dispersion forces for both of them, because this guy's got more electrons. Xenon hexachloride is the one that condenses first due to increased London dispersion forces. Which one is most likely to exhibit ideal gas properties? Carbon dioxide, because of its reduced intermolecular forces, meaning that these forces are pretty small. So even if they happen to get relatively close together, this is still going to be pretty small. Xenon hexachloride is a gas in a container. Circle the conditions that would most likely ensure no interactions between particles. So I want to keep them far apart. So that's low pressure. I want to keep them moving really fast and have a chance to interact. That's high temperatures. So I'm looking at a high temperature with a low pressure. A 200 milliliter sample of nitrogen gas is most likely to display non-ideal. Okay, so this is one again. Non-ideal means that there's going to be some interaction. So I want to get these particles close together, just high pressure, and I want to slow them down. So that's going to be cold temperatures. Okay, so I want high pressure, which is that guy, of those, and I want the coldest temperature ties to that guy, so just this one here. And B is my option. Alright, so we have 4 chemicals. I just drew this one on here so a person could know what benzene looks like. I'm not saying it's the answer. Which volume substances is most likely to violate the ideal gas law? So we're looking, in this case, for the one that's got the most increased intermolecular forces. Dipole moment 0. This guy's extremely symmetrical. Dipole moment 0. Dipole moment 0. This is the only one that doesn't have a dipole moment of 0. This is going to look likely like this. Something where it's bent. And we got these extra paired electrons here. So it's going to be bent, and that one right there will have a dipole moment. So that's my answer. Thank you very much.